So let me thank the organizers for the kind invitation and for this wonderful conference and for the opportunity to present some joint work with late Martin Dobek and other two collaborators, Lara Pexova and Jan Pullman. And it is about a relation between perturbation theory that mathematicians do in homological algebra and the perturbation theory, what physicists do in quantum field theory. So let me start with the mathematical side of this perturbation. So what people introduced already maybe in 60s. It's the homological perturbation lemma, and the starting point is that you have something which is goes under the name standard situation. So you have two differential graded vector spaces, V and W, with the respective differentials. This means they square to 0, Q and E as well. They are of degree 1. And you have a pair of maps P and I, which are maps of complexes intertwined between the respective differentials. They are of degree 0. And then you have endomorphism of V, the contracting homotopy, which is really contracting homotopy between the identity on V and the composition I and P, which is of degree -1. If, in addition to this standard situation properties, you have another one that if you compose P and I in this order, you get identity on the W. And even more, if you have these extra conditions that P and K compose to 0, K and E compose to 0, and K itself squares to 0, then, well, you call it special deformation retract. And what is the perturbation lemma about? So you start with the standard situation, like before, and you perturb one of the differentials, Q, by a small perturbation. So you add something of degree 1 so that the sum again squares to 0. And the perturbation lemma tells you that you can obtain, a new standard situation starting from the perturbation. And these are the explicit formulas. So you can form a new differential E prime using the above maps, the I, P, the perturbation, and the contracting homotopy. You get a new map P prime and I maps I prime and the new contracting homotopy K prime. And the formulas are simple. It's always geometric series, essentially. No, it just means that, that this geometric series would converge. But, well, since we are doing perturbation, well, it doesn't really matter because we take expansion and consider, order by order. So you can think of like some small parameter, let's say H bar multiplying this perturbation, or some coupling constant or whatever.
The condition B plus delta to the square equal to 0.
Yeah, it's really 0.
Repeated exactly?
Yes, it's exact. Well, actually, there is a version of that with the curvature, but yeah, today I will not talk about this, but yeah, there is another version which allows for curvature as well. Yeah. Good. So the claim of the perturbation lemma is, as I said, the perturbed data are again a standard situation if you started from a standard situation. Now, if your maps P and I's are quasi-isomorphisms, so this means isomorphisms on the cohomology, the perturbed one will be as well, and the same if P is surjective or I is injective, then also the perturbed one will be. Then, if you start with the deformation retract, so you will get again, if there is some condition fulfilled by the contracting homotopy and the perturbation, that's the condition. It's if and only if, actually. And if you start with a special deformation retract, you get again a special deformation retract. So that's the claim of the homological perturbation lemma. And since we are going to apply it to Batalin-Volkovitsky formalism, you know, what we also will have or will be useful to have is an odd symplectic form of degree -1. So now we consider our differential vector space graded equipped with this odd symplectic form. And this data actually gives you immediately a special deformation retract. So how you get it? You decompose your differential graded vector space in a piece which is isomorphic to the cohomology of Q. Then you have the image of Q, and you have a complement to the image in the complement of the cohomology. And how you construct the maps for the deformation retract. So P is obviously the projection to the cohomology. I is the injection. Yeah, and K, the contracting homotopy, is the inverse to the Q, I mean on the image of the Q. And actually, what you have automatically is that the cohomology itself becomes a symplectic vector space, so it inherits the symplectic structure, the odd symplectic structure from the space V. And also this complement has its odd symplectic structure, so these are just restrictions, both of them. And this image of Q and its complement are Lagrangian subspaces in this direct sum. So, well, this goes under the name of Harmonious Hodge decomposition. So this you have automatically once you have the odd symplectic form and a differential. So to be more explicit and to be kind of mathematically precise, I will assume for simplicity that my space V as a graded one, well, its components are degree-wise finite dimensional, which, well, of course, you can object. You never have this in quantum field theory. But, you know, you do the things, and then you look in the result, and then you forget about the assumptions, and you use it and see what it gives. Okay, so it's also kind of useful to be explicit and introduce homogeneous coordinates on the subspaces, on the cohomology, on the image of C, and on the complement. So this will be denoted like alphas, betas, and gammas, respectively. And since your symplectic form decomposes, then, well, also the inverse decomposes, and you use the inverses on the cohomology and on the complement to introduce Bartholomew-Wilkowski deltas. Okay, so sorry, there are two, there is a prime missing. So, and similarly, your Bartholomew-Wilkowski bracket also decomposes as a sum on the one of the cohomology and on the one on the complement. Well, actually, these operations act on the functions on my differential graded vector space. And, well, to be more precise, I should say, well, on formal power series with values in functions, and, well, should consider proper subspace, make sense of all the expressions which will appear. Yeah, these are some technical details. So I started with this special deformation retract coming from my differential graded vector space V and the odd symplectic form, and was here, right? And now, well, you can extend it using the so-called tensor trick of Heidelberg and MacLean to the functions on your vector space. And how you do it? So now, well, you have the functions on the vector space. This has a differential, which, well, in Bartholomew-Wilkowski formalism, it is just the Hamiltonian vector field corresponding to the free part of the action. And that's the explicit formula in these coordinates I introduced. So this is the matrix of Q of the differential. This is how you extend the differential from the vector space to the functions, well, using the Leibniz rule. And that's the formula for the extension of the contracting homotopy. Oh, sorry, there is, well, this x is too much, or there is missing x on the other side. As you see, again, it's formed by the inverse of Q. And it is not a differential now of the algebra of functions, because you divide by numbers of these coordinates betas and gammas appearing after you apply this differential. And there is an, of course, obvious way to extend the maps I and P to capital maps P and I. So this gives you a special deformation retract on functions. And right. Well, now actually I can come to the point about the homotopy transfer. So what I would like to consider is quantum versions actually of homotopy algebras of Lie infinity, A infinity, maybe even super versions of those. Essentially, everything which comes as an algebra over a Feynman transform of a modular operand. But, well, if you haven't heard these words or not familiar with it, well, doesn't really matter because there is a one-to-one correspondence between, for example, quantum L-infinity algebras and solutions to the quantum master equation. And actually, this holds true for all these homotopy algebras originating from Feynman transform of a modular operand. So maybe I should mention some names. Well, here, who told us this. So how does this actually go, the correspondence? So if you have a solution to the quantum master equation, so you can write your action as a power series, but in G, where you can think of G as of genus, and n, well, n is the n plus 1 is actually the number of, I mean, the n plus 1 monomial in fields appearing in the action. And since your symplectic structure is non-degenerate, this immediately gives you n-array operations, so which take n fields and produce a field out of it. So you have something with n inputs and one output here for each n and for each genus. And if you just plug into quantum master equation, this will tell you that there are some algebraic relations for these operations. And these algebraic relations for these operations, well, these are definition of quantum L-infinity algebra. So you have now kind of three definitions of, let's say, quantum A-infinity or quantum A-infinity or whatsoever. Algebra, either it is algebra over the Feynman transform of some modular operand, like that would be that would be commutative, and this would be associative, and for C infinity it would be the Lie, and etc. Or you can just say, well, these are solutions to quantum master equations, or another definition would be using these algebraic relations, which are equivalent to the quantum master equation. So now we know, well, actually, I should maybe comment a little bit on this. If I write the master equation this way, I need a bit more structure in general, because I should make, in these more general cases, like A infinity, or, well, different cases, in A infinity, C infinity, etc. Cases, I would need to make a product, a sense of out of the product to be able to write an exponential. And for this you need some more structure on these modular operands. You need something, well, which you can call connected sum, which gives you the product. And actually this is a subtle point. What you get actually is not really Batalin-Wilkowiski delta and omega, but what people would, like Kevin Costello and Owen Gwillian, and these people would call Bellingson-Drinfeld algebra. Well, and then, of course, if you forget about the genus, you get an L-infinity algebra, which you encode in the solution of the classical master equation. So what we are actually going now to do is, we have the free differential, and we are going to perturb the free differential and using homological perturbation lemma and see what happens. So what you can do, you can, for example, start with perturbation where you just add the Bartalin-Velkovisky delta to your free action or your free differential to the BRST. And, well, you take the formula which tells you that you get, you have this projection from your functions to the cohomology of the BRST operator. And that's the one, the new one, P1. Well, you remember this geometric series. Well, which is the one from the homological perturbation lemma. And you apply it to the interaction, the exponential of the interaction part of your action. And what you get is obviously something which is a function in the cohomology, and, well, a little work shows that it can be written again as an exponential of some W, a function on the cohomology. And actually, immediately from the homological perturbation lemma, you see that once you started from a solution of the Bartalin-Velkovisky master equation on the big space, you get a solution to the quantum master equation on the cohomology. And it's a little exercise to show that under this projection, you can rewrite the geometric series as an exponential of something which is the propagator. So, and this is the standard Feynman diagram expansion in quantum field theory. That's what you do when you compute the S matrix. Or actually, if you are in this kind of finite dimensional case, as I am, well, what you have here are finite dimensional integrals, and you can compute them explicitly. So you just, take your action, which is the sum of the free one and of the interaction, fix the gauge, put betas, these are actually the trivial fields, put them to 0, and yeah, just compute your integrals, and you obtain the same W bar. So, well, again, just confirming that what the perturbation lemma does for you, it does, computes the S matrix using either Feynman diagrams or Bartalin-Velkovisky path integral. And maybe you recognize here, like in this formula, this Lossev streak. So that was the first kind of perturbation you can do. Or actually, you can do with this first perturbation even more. Well, you can introduce effective function, not just the effective action as before, but for any function of your fields. Well, you just can apply again the formula from the homological perturbation lemma for this new projection, and what you get is the unnormalized path integral. So which produces your function on the cohomology. I'm sorry, there should be H on the cohomology. Now you can do another perturbation, so you can perturb your free action or your free BRST differential with the Batalin-Wilkowiski delta, but also with the Hamiltonian vector field coming from the interaction part. So that's another perturbation, and again, look up the formulas from the homological perturbation lemma, and well, you get a new projection. And well, of course, you can compare it to the first one. Well, it's almost immediate from the formulas. And well, what you see that the second perturbation, for this second perturbation, the homological perturbation lemma gives you directly the normalized path integral. Here you divide by the exponential of the effective action. And so you can compute the perturb differential. Again, you take the formula from the homological perturbation lemma, and you find out that the perturb differential will be now Batalin-Wilkowiski delta on the cohomology plus the Hamiltonian vector field corresponding to the effective action. Well, and there is no Q because we are now in the cohomology. Okay, I should mention that this in various kind of forms and examples appeared already before in some work of Carlo Albert and Owen William. They had some particular examples, but it works fully in general. Okay. Yes, related to this is a notion of homotopy between Batalin-Wilkowiski theories, or if you wish, since we know that Batalin-Wilkowiski theory is the same as a quantum L-infinity algebra, or with some times, depending on, yeah. So what you consider is you have now your functions still on your vector space, differential graded one, with the BRST operator and with the symplectic form. And you just tensor with one forms on the unit interval. And you consider like, yeah, elements here, which yeah, are either functions, always it is the sum of a function on T with values in functions of V, yeah, plus one form. Where now the B is of degree -1. And you say that well, this one form plus a 0 form is a homotopy between A at 0 and A at 1. If AT solves the quantum master equation for every T, and the time evolution of A is given like this, using the BRST, delta, and yeah, and B. Actually, once you impose this equation, then it's enough to assume that that A solves the quantum master equation, well, in one point, let's say in 0. Then the rest, yeah, for the other times, it will follow automatically from this condition. And what you can prove then is the following, that there are three statements concerning homotopies. So if you have two functions, like S0 and S1, then, well, the first statement is that there exists a homotopy between them. Well, and this is equivalent to the second one, that, well, essentially the difference between the exponentials is like Batalin-Wilkowiski exact with respect to Batalin-Wilkowiski operator plus the free action. This is differential, so this is yeah, this difference is exact with respect to the differential like Q plus H bar delta. And the third equivalent statement is that there exists a symplectic diffeomorphism starting with identity, such that if you take the semi-density formed by the action S1 and you pull back it with respect to this diffeomorphism, you get the one well, for S0. And so maybe there are few remarks. Well, the proofs are kind of standard. There is nothing special about this. So what is kind of surprising that the most simple homotopy which you can imagine, just the affine combination of the exponential, works. And of course, the diffeomorphism here is generated by the Hamiltonian vector field corresponding to B. You remember, B was the one which would govern the time evolution of the homotopy between S0 and S1. And actually, you can rewrite this so you can add the free actions and consider the difference of the volume forms and, well, show that it is exact with respect to the BRST differential. And, well, you may recognize some graded version of the Moser lemma, telling you that if you have two volume forms, yeah, which are in the same cohomology class, the RAM cohomology class, you will find a diffeomorphism relating them. Yes, so how does this relate to this homological perturbation lemma? So recall the first one we did. So we perturbed our BRST differential by Batalin-Volkovitsky delta, and we got a new special deformation retract with the new projection, injection, and the new contracting homotopy, and the new differential. And well, you just take this and apply it to exponential of the interaction part of the action. And what you get immediately, you get one of these three equivalent statements about the homotopy. You see that the difference of the exponentials of this effective action coming from the perturbation lemma and the original one is exact. Well, because the new Q1 is actually, well, the one which appeared in, exactly here in this second equivalent claim about the homotopy. So, in this case, the homological perturbation lemma tells you that there is a homotopy between your action you start with and with the effective action or S matrix, if you wish. And therefore, also, you will find the change of coordinates, a diffeomorphism, which would take your semi-density, which you use for integration in the Batalin-Volkovitsky. So the one you started with, and it gives you again the S matrix. And actually, if you look closer to this, it tells you that you have a decomposition, actually, decomposition theorem for quantum L infinity algebras. Recall, here, this solution to the master equation, quantum master equation, gives you a quantum L infinity algebra. And yeah, here you get another one. But here what you get actually? Here you get one part which is actually a function on the cohomology only. So all the higher operations for the quantum L infinity algebra here are just are non-trivial only on the cohomology, and you get the free part. So all the on the complement, you have just a differential and no higher operations. So this just tells you that, well, again, starting from homological perturbation lemma, that starting with a quantum L infinity algebra, you will always find an isomorphic one, which decomposes into minimal model. This is the part non-trivial on cohomology, and the contractible one. So maybe you know the statement for ordinary L infinity algebras or A infinity algebras. These have been proved using different techniques, like maybe some operatic also ones. Well, now you get it, well, essentially for free from homological perturbation lemma, and even for the quantum case where you have loops. Yes, so, right. Of course, this is something which you perfectly know from physics, from Batali-Volkovitsky formalism. There is actually no surprise. So what you actually have is a map which is Poisson, which intertwines between the, well, of course, actually not only intertwines, yeah, it preserves the symplectic structure, and it maps the original action in the S matrix and the free part. And it would give you one possible example of what you may call quantum L infinity isomorphism. So it is the diffeomorphism which intertwines between the two Batalin-Volkovitsky operators. And, well, you know that if you would like to see what it says about the actions, that it's not just that you have the one action is the pullback of another one, because, you know, you pull back semi-densities actually. And so you have this extra piece, this logarithm of the Berezzian, which tells you that, yeah, you are changing the volume form. And yeah, if you compose this one with the projection to the cohomology, well, you get this minimal model, and this is quasi-isomorphism. Yeah, so actually what we do in physics, we compute the quasi-isomorphism between our starting action and between the S matrix. Okay. Maybe it's related to what I told you. There is another nice example of the homotopy, which is the exact renormalization group flow. And again, well, I'm considering just a toy model, kind of finite dimensional, because, well, in the infinite dimensions, well, I should have told you, I don't know how to define Batalin-Volkovitsky delta, really, right? Because it's singular. So I would have somehow regularize it or renormalize it using, for example, Costello does in his book. But yeah, now, first of all, I don't know how to do it exactly. And to keep it simple, I stick to my finite dimensional case. And so you can introduce the cutoff and one parameter family of Batalin-Wilkowiski deltas. So remember, this is the piece on the cohomology. This doesn't get changed, but the one on the complement, well, will depend on the cutoff. And right, that's the dependence on epsilon. And from this, you immediately get the dependence on the cutoff of the propagator. And the exact renormalization group flow, now you can formulate as, a one parameter family of actions depending on cutoff, which depend on epsilon like this, and solve the scale epsilon Batalin-Wilkowiski equation. And obviously, everything is designed that you have this simple claim that if S epsilon prime solves scale epsilon prime quantum master equation, then well, it will solve the scale epsilon as well, quantum master equation. And this epsilon is almost a homotopy in the sense before. Well, from these two conditions, you get immediately the formula for the time evolution, for the epsilon dependence of the action. And except to this extra piece, where this is the operator which counts the numbers of betas and gammas. Remember, these are these homogeneous coordinates on the complement of the homology. It looks exactly like the condition from the homotopy between solutions of the master equation. Well, in my simple case, I just can bit rescale the action and get a true homotopy, which I couldn't do really in quantum field theory. But in the finite dimensional case, it works. Okay, so since I already mentioned kind of morphism and quasi-isomorphism between quantum L infinity algebras or Batalin-Wilkowiski theories, you may ask, well, what is the correct notion or proper notion of a morphism between quantum L infinity algebras or quantum A infinity or whatsoever? And well, of course, if you are a mathematician, you would like to have a model structure on the category of L infinity algebras. So that the quasi-isomorphism would be the equivalences in this model structure. So, well, if you start thinking, so the first thing is that you always have this odd symplectic structure around. And so you would think, just a symplectomorphism, you should start with a symplectomorphism. But this is too restrictive, so it's not, well, people know that already in symplectic geometry. If they would like to have the good category of symplectic manifolds, yeah, symplectomorphisms are, well, not good enough. Maybe you can say, okay, I just since I can always invert my symplectic form, get Poisson structures, I may think of Poisson maps. But this will go only always in one direction, right? So from, oh gosh, so you can always like embed a smaller one into a bigger one, but not project, right? Because you cannot make, like, you know, if you have x and pi's which give you one, the Poisson bracket, you cannot put x and pi at the same time to be zero. It wouldn't be first class constraints. So, well, this makes, you know, this would make kind of not symmetric, this equivalence relations or morphisms. But, well, what you can do, and what well, was the proposal of Chevera, and it's inspired by the Weinstein's symplectic category, is that you would consider correspondences. So what is the correspondence? You would take two symplectic manifolds. Now they are odd symplectic manifolds, and you can just do the Cartesian product like here, where you take the, let's say, the first one with the minus symplectic form, and you can look into Lagrangian subspaces here. And you would call that a Lagrangian correspondence or a morphism, because, yeah, there is a way to compose these things, obviously. That's what was Weinstein's proposal for symplectic manifolds, and its variation for the odd symplectic manifolds is with the Chevera. So here in our case, we want a bit more, because we would like not just relate the symplectic vector spaces, but also say something about the actions. And so what we should consider are half densities on the Cartesian product, which are supported on a Lagrangian subspace. And so since, well, I would like to make a category out of it, so I should tell you how I would compose such things. So if I have one semi-density on M1 bar cross M2, and another one, well, sorry, bracket missing, from M2 bar times M3. So what I can do, since I have M2 and M2 bar, I get something, a density on M2. So I can integrate over this density, which comes as a product of these two semi-densities on M2, and get the semi-density or half density on M1 bar times M3. And since we know that on half densities, on an odd symplectic manifold, we have a Batalin-Volkovitsky differential. So you can easily prove that decomposition of morphisms is compatible with Batalin-Volkovitsky delta. So, well, if you start with two half densities, which are Batalin-Volkovitsky closed, you get again a Batalin-Volkovitsky closed half density. So this leads us to the following definition. So what we consider is a half density on our symplectic manifold, which satisfies the Batalin-Volkovitsky, which is Batalin-Volkovitsky closed. Well, call it the solution to the quantum master equation. Well, you can think of e to the action, like, for example, times yeah, half density formed by the Lebesgue measure, for example. Yeah. So, and I say that a pair odd symplectic manifold with a solution to the quantum master equation, MF, and the other one, NG. Yeah, we would say that we have a morphism between these two pairs if we find the delta closed half density on m bar, cross n, such that if we integrate f against this half density, we get g. So, well, now an example, of course. Obviously, you would like to have an ordinary symplectomorphism to be a morphism in this sense, right? In this odd symplectic category. And, well, it is an example because, well, what do you do? What is your correspondence? So what is the Lagrangian subspace here, which you consider? In this case, you just simply take a graph of your symplectomorphism. So this is obviously a Lagrangian submanifold here. And now I need my half density. Well, and it's simply just the delta supported on the graph. So this, well, and what is it? It's exactly the morphisms, yeah, which relates the, well, solution of the master equation and the pullback. So, well, it works for the obvious example. And there is another example coming from what I told you about the homological perturbation lemma and Batalin-Volkovitsky path integral. You remember, well, the construction leading to this minimal model or to the S matrix on the cohomology. So you had this decomposition. Oh, sorry, there is a circle missing in the cohomology image on Q and the Lagrangian complement. And you would like now have a morphism between your original quantum field theory on the space V and the one on the cohomology and the S matrix in this language of half densities supported on the Lagrangian submanifold. So, well, of course, what you should consider is, well, that's the definition, as half densities on V bar cross H. And yes, well, and it should be supported on the Lagrangian subspace. So the obvious thing to do, you have the Lagrangian subspace here, which is the C plus the diagonal, because you have two copies of H, one here and one here. So you take the diagonal, and you take delta supported on this Lagrangian submanifold, and look back to the formulas I showed you coming from the homological perturbation lemma, and you see that that's exactly what it should be. You integrate your original exponential of the action in the Batalin-Volkovitsky path integral against this delta, supported semi-density, and you get effective action. Sorry, that should be volume form on the cohomology. Yeah, so this, well, the hope is that if you reformulate this now in the language of quantum L infinity algebras, you might get a reasonable notion of a morphism. Though, okay, the point is that the symplectic category or post-symplectic category, it's not really a category in the sense that it should be, because you can always compose morphisms, but it's not obvious that you always get a morphism. So, but there are ways of course, there are well-known conditions on that when it happens, and there is a way how you can complete it or extend it, adding everything which is missing. So you do the composition, you get something which is not, because you don't need necessarily get a Lagrangian submanifold in general, but you can add it, and you can continue and see what everything you have to add it. And there is some interesting work even in the symplectic case with no battalion Lokovisky. People like what are the names? I'm sorry, Woodward and yeah, thank you. They extended actually to a 2 category, and well, they have some nice application for the floor homology. So it seems that there is some room to play with this, and well, see what you get if you think it's kind of interesting. Okay, that was all. Thank you very much for your attention.
Okay, thank you so much. Are there any questions?
At some point, you described a morphism, a quasi-isomorphism between actions. What was the quasi-isomorphism?
Oh, the one you know that it exists from the homological perturbation lemma, because so the logic of my claim was that you have these 3 equivalent statements, that there exists a homotopy between 2 actions, between 2 battalion Lokovisky actions, or the difference is exact in some sense of the exponentials. And the third one, there was a symplectic diffeomorphism between them. Now, from the homological perturbation lemma, you immediately got the second one. Just looking into, applying the new special deformation retract you obtained from the perturbation lemma, and it just immediately did give you like the second statement, that the difference between the exponential between the effective action or the S matrix and the original one is exact. And therefore, there will be diffeomorphism going between half densities. And if you take this one and project it to the cohomology, you get a quasi-isomorphism. Well, it's again guaranteed by the perturbation lemma, which tells you if you start with a quasi-isomorphism, then you get a quasi-isomorphism.
And yeah, also on this theorem, that half density, is that part of the data of your BB theory, or is that?
Oh yes, but now since I'm in just a vector space, it's just the Lebesgue measure, the unique one, translationally invariant up to constant. But otherwise, of course, that would be part of the data, obviously.
So I have maybe a question about this version of the symplectic category.
Yes.
So I guess the idea of Lagrangian subspace comes up in a lot of ways, and one that I know is that you told me PV theory, and you look in codimension 1, then the space of sort of boundary values of fields are now unshifted symplectic, and on the branching in there, we'll define a boundary condition for that field theory.
Yeah.
And so I could use something like this, for example, to talk about an interface between two field theories. I could think about restricting the fields and asking for an unshifted Lagrangian between these two spaces of boundary fields. And sometimes people like to think about this as maybe being some kind of morphism between two field theories.
Right.
But you're suggesting something, I mean, in your category, something is like a Lagrangian in a one-shifted.
Yeah.
Minus one shifted, rather.
Right.
Space. Right. I was wondering if there was any relation, or if you have some physical intuition for that.
I don't know. Well, actually, what it should give in the, let's say, forget about the quantum, just think about the L infinity, or like the classical master thing, then what you can easily do, you know, you have two master actions, classical master actions. Well, then you can pull back it to the product, to the Cartesian product, and push, yeah. And, well, you should get, well, the difference, well, they should be equal, right? So it's kind of duality in a sense, right?
Yeah.
You have two things which come from something common upstairs, yeah. Which was this half density, right? You used to integrate. You take one, integrate it against, and you get another one.
So I guess in that classical limit, this will define something slightly more general, like an L infinity morphism between two.
Right, yeah. Yes, because now, you know, if you just think about L infinity, you don't have to care about the symplectic structure, so it's slightly something different, right?
Right. Maybe there's some way that if I say cyclic L infinity.
Yes, cyclic, yes. Yeah, you would have to take, yeah.
But, so, I mean, even if I just think about symplectic vector spaces, there are slightly more correspondences than there are graphs of maps.
Yes, definitely, yes.
So. Okay, thank you so much. Are there any other questions from? Your format? I don't think so, so now let's thank the speaker again.